Okay, just a reminder, if you ever have issues with the Google Classroom, like let's say I don't post a video, I forget to post it, or I post it and the link gets corrupted. Sounds so evil. If you go to my YouTube channel, so just click on any one of my previous videos, click on the channel, and then go to videos. You can probably go to playlists. Where's playlists? Right there. And usually like, for example, grade 12 right here, this one says polynomial functions, right? This one that I'm hovering over. And so if you click on that, all the videos are kind of just based on this chapter. And so all of the videos that we've done in this chapter, I'll just place them in there. So if I ever, and please let me know when that happens, I can fix it, but sometimes you can't reach me. And so that's the quickest way to get to it. All right. Word problems, guys. This is where everything changes. Okay. So let's go through this one. This one is kind of extensive, so let's go through it. The path of a baseball that has been hit can be modeled by the following equation. Emphasis on modeled. Okay. It's going to try its best to kind of tell us the path of that ball, right? So this is the equation where h of t is the height and t is the time in seconds. Can I just ask you to do this right now? We now know, based on the equation, that x stands for time and y stands for height. That's very important to remember. Okay, I will never trick you on that, but now you know that a coordinate stands for time and the particular height at that time. Okay, so you will notice that you're finding the x-intercepts, you're finding the y-intercepts, you're finding the vertex, all of those things, but now they have a meaning. What's the initial height? Okay, what's the initial height? This is important. Of the ball, right? What was the ball first hit, right? This is given to us by the y-intercept, right? And the y-intercept is 0, 4 based on that equation. It basically gives height at time of 0 seconds. Okay. So I don't want you to just tell me 0, 4. Mr. Dirksen, 0, 4, that's it. You have to be specific, right? Initial height is equal to 4 feet. Okay. You need to tell me exactly which one of these two numbers is answering the question, not the coordinate. Don't give me the coordinate. You can write it down, but then actually give me the number that answers it. Determine the maximum height of the ball. What do you think you're going to have to find? Based on the leading coefficient, we know this one is pointing down, right? So the maximum height will be obviously at the turn, right? The highest point, given by the vertex, right? Given by vertex. So we're going to go second trace max in this case. Okay, so let's go ahead and do that. I'm going to clear everything else. So negative 4.9 x squared plus 35x. We don't have t's, right? All we have is x. And we're going to graph this thing. And I can clearly tell that my window needs to be adjusted. So if I look at my window, when I graph it, this is overkill, right? So x max could be 25. X min is overkill as well. I'm going to go higher to the 50s for my y max. Still not high enough. One more try, 100. Perfect. There it is. I need to make sure you understand this is not starting on the ground, correct? A lot of students, when they go ahead and graph it, this looks so close to 0, 0. It's 0, 0, right? You got to make sure you understand that, right? So second trace max, it's asking you for a left boundary, enter, right boundary, enter. So now we narrowed it down, and there it is, 3.57. So write it down. I actually encourage you to do that. And it's 66.5. So us knowing that the first number represents time and the second is the height, In this case, the max height is 66.5 feet, right? You gotta give me units, don't just give me 66.5, right? Everything now has a meaning and has units. How long does it take for the ball to hit the ground, right? This is given to us by the x-intercept, right? Height is equal to 0 there. So we're going to go y2 is equal to 0, second trace intersect, and that's how we're going to find it. So let's go ahead and do that. This is it. From time to time this happens. So some students are like, oh, I'm going to find the first one that's negative 0.11. Don't do that. For us, negatives are not considered because we're dealing with time. It can't be negative. So all we deal with is the other one there. That one. That's going to tell us how long it took to hit the ground. So 7.26. Remember to round. 7.260. So it takes 7.26 seconds, right, to hit the ground. And you know me already, I don't need like a whole sentence necessarily, just a short little indication that you know what the answer is. Exactly. You don't just give me that. You actually just quickly tell me, hey, it's this one. It's that number right here, the first one, the x value. Calculate the height of the ball 1.5 seconds after being hit. So this is a question where I want you to think of it this way. This is 1.5, and they want to know the height, right? They want to know the y value there. So we're going to go second trace value, x is equal to 1.5, okay? So we're going to second trace 1 for value, and saying, hey, if time is 1.5, what's the height going to be? And there it is. It's telling us that it's 45.48 feet. Y is equal to 45.48 feet. I'm okay with that, right? You're saying, hey, I know that it's the y value, which represents height, which is in feet. I'm okay with that. Okay. Sorry if I'm going a little fast, but I will assume that you know most of this already. Okay. Determine the time the ball remains at or above 49 feet. Here, I want to slow down a bit. A question like this is going to be worth 2 marks. Okay. Time at or above 49 feet. So we're going to do this. Okay. Let's go ahead and type in, we're going to go to y equals. We're going to focus on a height of 49 feet now. So I'm going to go y2 is equal to 49, hit graph, and there's that 49 feet line. So we want to know how much time went by from when it first hits 49 feet and it keeps flying, right? And it comes back to that 49-foot mark. So how much time went by? Some of you will remember this, right? So I kind of just do this. It doesn't start on the ground, right? It goes like this. And here's my 49, right? This is 49 feet right here. Okay. And we're going to find the 2 instances, the 2 times that happens. Because if I figure out the difference between these two, I can figure out the time that it's spent at or above 49 feet. So we're going to go second trace intersect. We're going to find it, like I'm going to do the second time that happens here. Enter, enter, enter. And that's 5.4613. I'm using 4 decimals here because I'm going to use them in a bit. I'm going to subtract the 2. So you find that. You go second trace 5 again to find that the first time it happens on its way up. And that's 1.6816. Just making sure. Yeah, we're good. 1.6816. I apologize for the lack of room there. And I will just say once here, y2 is equal to 49. And then I went second trace 5 to make that happen. Give me the keystrokes. Let me zoom into that part. I'm going to zoom in because we don't need the grid just yet. Okay. That's 1.6816. That's the first time that happens. And then it happens again here. So I don't know, you probably remember this if you took physics or science, or any sciences really. Delta time tells me, hey, what's the difference between those two times? So I will say it's this. I will subtract them, right? Because if you subtract that, you get the time that elapsed between the two. Okay. Take your calculator. Make sure you use 4 decimals, because if you don't, you could lose a mark for rounding too soon. And that's when you round to 2 decimals, 3.78. 3.78 seconds that went by. And I will highlight that, okay? So this is the time that was spent on this little stretch up there, okay? I don't have room for this, guys, but what if the question asks how much time was spent below 49 feet? It's kind of like indirect reasoning. Time below 49 feet. If it said below, you know that the total travel time was 7.26, correct? If you were to subtract that time from this, right, that must be the time spent below 49 feet. So I don't have time for that here. I don't have room, never mind time. So I will leave this for now, but it will come up. I'll make it come up on ACs and stuff like that. So just watch out for it. Let's graph the scenario. And this is where what we've been practicing since last week, Friday, or even earlier, how to graph, right? So you need to have your important points in here. And notice that I was kind enough to tell you, hey, this is quadrant 1, right? I don't want to see anything going into the negatives here, guys, because you're going to lose marks immediately, okay? So here's your axes. We're going to call this time, and you got to give me the units, because you're still going to lose marks if you don't give me the units, okay? So time seconds. At the top, it's height in feet. And a lot of you should have no problems with this. You should be really good at it. Because I did a lot of graphing in grade 11 applied, right, guys? You're sick and tired of it. But you were really good at it at the end, I know, right? I've marked your stuff. It was easy to mark. And so I need to make sure that I allow for my x-intercept to fit. So 2, 4, 6, 8, yes, that works. I'm going with that, okay? A scale of 2, it's not really a scale of 2. It's a scale of 0.5, right? If you think about it, 2 divided by 4, every box is worth 0.5, but you're consistent. Here, I need to make it all the way to 66.5, right? The highest y value is given to me by the vertex. So 10, 20, 30, 40, 50, 60, yeah, that's cutting it a bit short. So I'm going to go 15, right? 15, 30, 45, 60, 75. That will do the trick for me here. I don't like it, but I have to make it work, okay? Let me zoom out just a little bit. And then you plot your points. My y-intercept is 0, 4. So this right here would be 7.5, right? Between 0 and 15. So somewhere here, as long as it's not by the 0, 0 point, right? And then the 7.26, this would be 7 right here. This would be 7.5. So 7.26 is right about there. Right, so you kind of have to do the half-half, right? Split your intervals. So it's right here. And then the vertex is at, 1 second, 3.57. That's why it's important to write down your coordinates, guys. right? I wrote down my coordinates of the vertex because it will come in handy when you're graphing, okay? So 3.57, this would be 3, this is 3.5, so it's just over. So 3.57, and I'm going to go up along that line. This would be 67.5 actually, right there on the line. So I'm just going to go below it. You can fool me on those a little bit, but if it can be exact, you cannot fool me, right? Like if I know it's supposed to go exactly here, you need to get it right. And then you go up, curve in, right, turning point, and then it comes down. In this case, it does touch the ground. There's no indication that it doesn't. Notice what I'm saying, right? In grade 11 applied, we did. And you will see that later on that you're hitting, it lands on a surface of some sort as being caught. And so then the graph would not touch the ground. Do not have this going on, guys. Don't do this right now. Don't copy it. But this cannot be there, okay? This cannot be there. I don't know if you want to do this as a reminder. You cannot have those arrowheads going into the negatives, right? Height could from time to time be negative, and you will have examples where it goes below the ground, like there's a roller coaster example. There's a bird, right, diving down for the fish, right? But in general, right, for sure, time will stay positive. Distance usually is positive, so keep that in mind, all right? I want to make sure I finish this example. Okay, state the domain and range of this scenario. We assume that the ball stops upon hitting the ground. The question must give you a bit of an indication as to when the action stops, or else it would go indefinitely, right? So we're basically, can I say something? We're coming up with restrictions to this function. We need to restrict it because we do not want to include everything. So it models it here, but below that, before or after, it doesn't do a good job at it. Like it continues on forever, which is not convenient to us. So that's what you're doing. So the domain in this case is from time 0 all the way to when it hits the ground. I love interval notation for this because you don't need to worry about the variable. You just write down the numbers. Okay? You don't have to worry about open brackets unless it's infinity. Okay? And then the range would be, this is where a lot of students get this wrong. They're, hey, 4, all the way from 4 to the highest point, but it does hit the ground. So technically 0 is included here all the way to the highest point, which is 66.5 feet. Okay, so I told you domain and range will change. If you are brave enough to go set notation, you got to use the squiggly brackets and you got to use the variables in question given by the equation. Okay, if you are brave enough to do that, and nothing wrong with you going with that, you need to make sure you use the variables given by the function, right? You got to go with those. Okay, you can't go x and y. You have to go t, h, or whatever k, whatever variable they throw at you. That's the one you use. Okay? Now there's a what if. What if? Okay. State the domain and range of this scenario, assuming that the ball was caught 6 feet above ground. So I want to do this on the graph. I normally don't like doing this because the graph is done. You don't mess with it anymore. But this would be 7.5. Like if this is 4, 6 would be just a little higher, right? Let's make a dot and highlight that with the same color. Yikes. That's a big dot. Okay. Anyways. I need to figure out if this is the 6 foot, this is the 6 foot mark. I need to figure out what the x value would be at that point, right? Because I'm assuming that the action will stop there. So when I give you partial information, you're going to figure out the x value, right? So I will ask you this. So this is basically question mark 6, right? That's the point. So y2 is equal to 6. Second, trace 5. And this will be one of the last things we do here before we part ways. So I'll clear that, make that 6, hit the equal button. There it is. So second trace 5, enter, enter, enter. That's 7.09. 7.09. So I'm going to write that down. 7.096 is that point that I just found. And let me write it in here as well so that it sticks out. 7.09, there it is. So you're like, what's the big deal? Well, my domain now goes from 0 to when it's caught, which is 7.09. And it's a little different than the previous scenario, right? And then the range would be what? What's the lowest height I ever get to under these new circumstances? 6, this would be 4, right? So the lowest height I ever get to is 4, and the highest I ever get to is 66.5. Okay? Why did I do this? I didn't want to have to do a whole nother example to just show you that, this is what happens when things do not hit the ground. Okay, ball doesn't hit the ground. And I know you're not going to write this down, but I want to talk about it. Write another equation that would model the path of a ball with a lower maximum height. What could you change to make that happen? The y-intercept, the last value here. If you wrote the exact same equation with a 3 at the end, it would bring the whole curve down, right, by 1. And so that would be a lower maximum height. So I'm going to do this real quick. Example, ht is negative 4.9 t squared plus 35t plus 3, right? So I highlighted that. I will add this to your notes tomorrow if you're already packed. This is your, I want to start homework. So I'll post that on the, I want you to try the one right next to it. Page 26, can you remember that? I'll put it on Google Classroom as well. Give it a try.